no stoplights, everybody goes. Some people tell me that there are some countries with actually things like this happen. Anyway, no accidents. No accidents here. This is taken from Peter Stone's website. So here is a nice application for you. Okay, let's do a little bit of math. There is much, much more math yet to be done. I would like to say that, you know, this area is now growing. Every year you see many, many, many new algorithms, but many of these works, or most of, we still, I think there is a big open question to really understand the nature of this problem. What is the complexity? What are the parameters that influence the hardness of this problem? Yes or no, and so on. But I would like to say that there is a very interesting continuum here. Okay, take the left side. One agent in a map wants to find a path. Nathan just discussed a whole bunch of techniques that are designed for, I have a graph, I have one agent who wants to go from one place to another. Go to the other side and you see the sliding tile puzzle. Think of it as you have 15 agents. Each one of them wants to find a path to its goal. There is only one blank. Okay? So if you go from left to right, you have the graph, start and putting more and more agents. Okay? That side is polynomial domains. We know a lot of techniques on that side. Take the right side, this is exponential domains. Okay? We have a lot of techniques from there, but start taking away agents. Okay? 1 blank, 2 blanks, 3 blanks, more and more and more. Then you see there is a whole continuum. So we are polynomial on one side, we're exponential on one side. What do we do in the middle? Or can we point to a point where, okay, here you're exponential up to here, you're polynomial up to here? Of course we cannot, but how do we take ideas or complexities or everything we know on the both sides and try to bring them together into the middle? This is a very interesting and open question, and more importantly, can we take all kinds of bounds and theoretical understanding on both sides and try to bring them together from both sides? Just to show you how tricky everything here is multi-agent pathfinding polynomial or exponential? The question is polynomial and exponential in what? Okay? The graph, let's say the graph is, we have a graph of n, and it's an explicit graph. Polynomial, d to the m. And we have k agents. Now, if you fix the map, but you add more agents, okay? So the size of your state space is s equals n to the k, which is actually dm to the k. It's exponential in k. Every agent that I add, my state space of how can I place all the agents in the graph, this grows exponentially. However, if you fix the number of agents, but increase the depth of your graph, okay, then this is polynomial in d, because m and k are constants. Okay, so this multi-agent pathfinding is in some sense exponential in the number of agents, but it's polynomial in the depth of your graph. So it's like some kind of a hybrid of both domains. Okay, how do people solve multi-agent pathfinding? And there are many, 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 many approaches, and we certainly need some taxonomy here, because many times you see people comparing, like, I have experiments, I have this, compared to this. You are in different classes. You are not even comparable. You are faster than him, yeah, but the solution you get is completely larger. You cannot not directly comparable. I'll try to introduce some kind of taxonomy here. So, naturally, we have non-optimal solvers and we have optimal solvers. Non-optimal solvers, you could divide them to search-based suboptimal solvers and to procedure-based suboptimal solvers. And there is a new direction which is now taking attracting more and more researchers, what I call reduction solvers, where they take multi-agent pathfinding and reduce it to SAT or to infinite. We work both for non-optimal and to optimal solvers. I would like to cover each of them very fast. Okay, so search-based suboptimal solvers. Usually what they do is that agents are planned individually, but of course when I plan the next agent, I have to make sure that it doesn't conflict with the previous agent. These methods are usually rather fast to run. They're easy to understand somewhat. However, solutions they produce are not optimal or suboptimal. Sometimes they are not even complete. Okay, so they forfeit optimality and completeness in order to obtain practical runtime. A canonical example is property A star and its enhancement. And what I do is I take the first agent, plan a path for it, and then I do reservation. Okay, some kind of reservation table. I reserve my path. Now the next agent has all path is of course a set of locations and you have the time dimension. The next agent plans a path, but he knows I cannot be at the same location, same time that is already reserved by previous agents. So you add more and more agents, you get into the reservation table gets larger, so the last agents will have it will be more problematic for them to find path. There are many enhancements, and of course you could see that this method is not complete because I can give you many examples. The first agent block the way to all the others, and they cannot go. You have to do some kind of backtracking, which is not introduced into these methods. Another set of ideas that people have been doing is to take many of the optimal solutions, either based on A star or on some new algorithms that I will describe, and do just what weighted A star does to A star. Do some kind of relaxation, don't look on all the search space in order to find solutions fast, but they are of course not optimal. In fact, we just have a paper on this this year at SOX where we took CBS and introduced CBS epsilon to that. I will talk about CBS later. Procedure-based suboptimal solvers, that's another set of algorithms. They are not doing search. They are using macros. Okay? Each agent is being told what do you have to do. Usually these algorithms are designed to get complete and fast. Okay? I want a very fast method and complete method to solve the problem. An example of exponential domain is Rubik's Cube. Okay? Everyone knows that you can use macros to solve Rubik's Cube. The question is, what macros can I use in order to solve multi-agent pathfinding? Okay, I want fast and complete path. Of course, they are far from optimal, but on the other hand, they can solve very large problems very fast. In fact, there was an old paper from 1984 which proved a polynomial time algorithm to pebble motion problem, which is a special case of multi-agent pathfinding. It was more a theoretical way of showing here's how I do the moves and everyone will go to their place. It was recently implemented by Cernic. Agents move one at a time, but the solution quality here is, in many cases, especially when everything gets very dense with agents, is far from optimal. There are a whole bunch of techniques that are doing similar things. There is a slidable multi-agent planning by Adi Botea and his student. In some grids with some attributes called slidable, you can tell every agent where to go and everyone will get to their places very easily. There is a push and swap family of algorithm, parallel push and swap, push and rotate, where when you have some macros, and every time you take like 2 agents or a little bit more and tell them, okay, here's how you should swap your positions, and in the end, we can prove that it is complete, and we can produce a solution fast, but this is, of course, far from optimal. Another variant is by Korshield, and Nathan and Rob were co-authors here. Very similar to push and swap, and this is complete for trees. But all these methods are not necessarily, they do not know the quality of the solution, they just want solutions fast. So it is really problematic to compare. I see sometimes papers where people take, I have a new algorithm and they compare it to an algorithm from the other side, from another group. It's not directly comparable because you want a complete method fast, so you compare running time. Yeah, but your solution quality is much, much larger, and you compare it to someone whose solution quality is much faster, and he's a search-based algorithm. So I would really want that, the taxonomy here should be more formalized and well understood by others. So let's not compare oranges to apples. Reduction solver, this is a new direction that is now been taken by many people. Let's reduce it to other known problems. Multi-agent pathfinding is very easily reduced to SAT. You know the variables are the agents, the constraints, you have constraints, so you can very easily transfer them to known problems and then use solvers that are designed for those problems. You have a bunch of examples from the recent 2 years only. These ideas in general work extremely fast, but for rather small graphs. When the graph becomes large, they are like in a SAT solver, when the graph becomes large, you will get many constraints and variables, and the SAT solver will just not be able to solve it. But on very small graphs, they can significantly outperform any other of the methods in the sense of how fast they find a solution. Yes?
You have a proof that multi-agent pathfinding is
Yes, yes.
what is it based on?
There are a number of proof of that. Nathan, do you want to comment on this?
You're right. Go ahead.
Okay, you know, tile puzzle reminds of multi-agent pathfinding. It's a special case, so this makes some variants of multi-agent pathfinding NP-complete. But there is a recent proof also, comes also from the pebble motion, that the problem is NP-complete. And the question is again, where is the exponential side here? And let's talk about this afterwards because it's more complex. Okay, but there are proofs. Cernic has another more general proof. Yes, that's right. Okay, let's talk now about optimal multi-agent pathfinding solvers. Okay, I would like to talk about two classes: A*-based approaches and other search algorithms. All try to find optimal solutions. And of course, when we want to find optimal solutions, we know in advance that we will probably not be able to solve large problems, and we have a scaling problem, but this can influence and can inspire us to then develop suboptimal solution algorithm based on those algorithms. Okay, so let's talk about A* approaches. The state spaces, of course, very easily. Permutations of all the k agents into n locations. So it's exponentially in k. Let's use this specific example. You have the two agents, the mice, they want to go to the cheese. Heuristic function, let's take a simple heuristic function, which is called sum of individual costs. That's exactly Manhattan distance in the tile puzzle. I'm taking every one of them, of the agents alone, and assume that no other agent existed. What is the shortest path? In fact, I can pre-calculate it. Once I know my problem, the graph is rather small, then all I have to do is k searches on that graph. It can be done very easily. In this example, the heuristic, we call it SIC, sum of individual costs. In this example, SIC is 6 because each of the mice here needs to go 3 steps. Okay? However, there is a bottleneck here at node C. There is a conflict. The optimal solution is that one agent should wait, let's say at node A1, and then go like this. And so the optimal solution is actually 7. One of them has to wait, so we will only get at time step 4 to the goal. So 3 plus 4 is 7. And let's work with this example. The problem with A*, okay? The state space is too large. Sometimes the graph is very large. Let's abstract the underlying graph. So Ryan has done this. He abstracted the graph, and I'm talking not about the search space that the A* runs on, but the underlying graph into known shapes. This is very related to what Nathan said. If I see like a corridor, then I can abstract away, I can contract away everything, and I'm replacing this with a corridor. And he had specific expansion schedule for these cases. However, sometimes this will produce a non-optimal solution. But you can, in many cases, if you have these shapes, then the graph dramatically becomes smaller. Another problem is that the state space is exponential in the number of agents. Okay, let's reduce the number of agents. How can we do it? Let's do independence detection. Now, we divide the agents into independent groups, which means there are no conflicts between the two different groups, and solve each group separately. This is a very smart enhancement when possible. Of course, the problem is how do I find this independence group? And Stanley in 2010 introduced an algorithm that starts to find independent groups, not all of them, but when he finds independent groups, they can be solved separately. So for example, if I add another agent here, so I have 3 agents, here is a 3-agent problem, but I have 2 independent groups here, so let's solve 1 agent and then the 2 agents. I certainly reduce the exponent here because now I will run at most in the largest group.
Is this similar to disjoint PDBs in the sense that each agent is one PDB and you make the
It's based on the same principle, correct.
Can you use the same techniques to find the disjointness? Which groups are independent of each other? Which patterns, which collection?
It is a strong reminiscent, yes. In fact, you might take ideas from here and here and put them together, I'm sure. Another problem with A star is that the branching factor is sometimes exponential, okay? Let's say I have 20 agents on a grid, and each of them can go to the 4 cardinal moves plus weight, so the individual branching factor is 5. So now I have 5 to the 20 different children for just a given node. See how big this number is. Let's reduce the branching factor somehow. There are one algorithm that does this is called M star. It dynamically changes the branching factor. So what it does, I'm starting with single agents. As long as I don't see conflict, I'm just having the branching factor is very small. When I see conflicts, I have to go back and work on a more on a larger state space with more agents. I'll give you a fast example. What M star does is it goes like this. Okay, I will only move each agent to one location as long as I'm good. I'm moving towards the goal. So the branching factor at the root here is only 1, although it has m squared different children, all the combinations between the AI nodes and the BI nodes. I'm going again, and there is a conflict. I cannot go anymore in this direction. So I'm going back, and only now after I find a conflict, I'm going back to the common ancestor of this conflict. In this case, it's the root, and I'm now increasing the branching factor. But if I found a solution when the branching factor was small, then I gain a lot by not generating many, many states. Surplus nodes, okay? We talked about this in the first half. How do I avoid generating nodes and putting them in open lists that I will not need them in the future? And because the branching factor is very large, the amount of surplus nodes is also very large. So we have what Stanley called operator decomposition, which means I'm only doing one agent at a time. So my tree will be deeper, but the branching factor will be much smaller. Sometimes I can stop without generating all, actually the nodes in the combined or the K agent state space. And another technique we described previously, enhanced partial expansion A star. My student, Mary Goldenberg, who actually now is receiving his PhD. There is, right now, in these very minutes, there is a ceremony. Unfortunately, I'm here. I sent him an email an hour ago. Anyway, he showed how enhanced partial expansion A star can be applied to multi-agent pathfinding, and the branching factor or the amount of surplus nodes are reduced very fast. I would like to cover in what's left new non-A star algorithms, all done by my student Guni Sharon. They are search-based algorithms, but not A star, something else. Okay. all these algorithms are exponentials, but they're exponential in different parameters. So the first algorithm is ICTS. We have 2 levels. The high level asks questions in this form. Is there a solution with cost 10, 10, 10? I can take the heuristic of the start state, and I know that each individual agent must at least go 10, 10, 10. So I'm asking, is there a solution where he goes 10, this goes 10, and this goes 10? This goes to the low level. Low level now tries to find, is there indeed a solution? And it is concentrated on this question only. I will not describe the low level here, but let's say that it says, no, there is no solution of 10, 10, 10. So the high level says, OK, how about this? 10, 10, and 11. Now the low level says, yes, there is, and here is the solution for this. So in fact, the high level works on a tree which goes like this. If the SIC was 30, 10, 10, 10, so I'm asking all possible combinations of 30, is there a solution? There's only one combination of 10, 10, 10. So I'm actually going a breadth-first search on this tree. Is there a solution of 10, 10, 10? No. How about 10, 10, 11, 10, 10? How about 10, 11, 10, and so on? And I'm going this until I find the goal node, and it's easy to see that this is will return an optimal solution. And the depth of this tree we call delta. It's the delta between the heuristic of the start state of the SIC, the individual cost, to the actual solution. Now, it turns out that ICTS runs very well on some domains, like on Nathan's maps, much better than all the previous A-star domains, but there is also pathological cases where ICTS collapses. This is exactly where delta is very large. Take a look at this example. The agents A and B need to swap their locations, but in order to do this, they have to move all the way around to the end of the corridor to switch the places. Delta here is 72, because SIC is 2, but the solution here is of length 74. A-star does this very fast, and the state space is not very large. All I have to do is all the combinations of placing 2 agents in this corridor squared, that's all. But ICTS, because of this delta, keeps on generating all these questions, and you could see that what A-star solved in 51 milliseconds, ICTS, it needed a factor of 1,000 more time, just on this example. So there is no universal winner here. The third algorithm that I want to describe is called conflict-based search, also by Guni Sharon, and Nathan here was a co-author here, and Ronnie Stern is also around in all these works. Let's look at A-star. What is he doing in this problem? Okay, A-star, the root is S1, S1. Expand it, it has M squared, all the combination of the AI nodes with the BI nodes. It has to generate them all and expand them all until they all try to generate node CC, but there is a conflict. That node is illegal. So for F equals 6, A-star goes by F. For F equals 6, all M squared combination of AI, BI will be generated and expanded, only to realize that there is no solution of length 6. So now A-star starts to look on nodes with F equals 7, only to see that there is a path here. But if I could identify that CC is a bottleneck and there is a conflict here, can I reduce the amount of the polynomial work that A-star does? This is the motivation for conflict-based search. Okay? What conflict-based search does, it plans for single agents, but under constraints. Okay? So every time the actual search is done on a single agent level, but I'm adding constraints to the game. As follows. Let's define a conflict very trivially. A conflict is 2 agents at a location at a given time. If they happen to be there, that's a conflict. A constraint is that I'm telling an agent, for agent A, do not be at location X at time T. So if I have a conflict, which means I see 2 agents at the same location at the same time, then I can resolve it by adding constraints. And either I'm telling agent, listen, you are not allowed to be there at time X, at location X at time T, or agent B, or I can tell it to the other agent. So the general idea for CBS is I plan for each agent individually, I validate the plan. If the plan's conflict, I'm taking the conflict and I'm branching according to one of these constraints, either by telling agent A, you're not allowed to be there, so replan your path such that you are not using this, you are constrained not to be there. In order to be optimal, there is also another possibility, do this to agent B. So this is how it looks like. I'm running here on what we call the constraint tree. It's a set of constraints for each one and a set of paths. So at the root node, I have no constraints. Each agent finds its own shortest path. Now I'm trying to validate them. So I'm going like this. I'm validating them on the time. There is a conflict at location C at time step 2. So I branch two ways. Either constraining in the left side, constraining a node, constraining agent 1. You are not allowed to be at location C at time step 2. So replan. I'm symmetrically doing this at the right side. In this case, when I'm expanding it, this is the goal. When I'm validating it, there is no constraint here, so I return this solution. It is easy to see that this is optimal. But if I want to analyze it, it turns out that while A star is doing here M squared states, CBS here is, because it's doing everyone separately, so it is doing linear time here. On this specific example, it is much faster. On the other end, we have another example of this open space where CBS is exponential in the number of conflicts, while A star is exponential in the number of agents. CBS expands here 54 states, while A star expands here only 8 states. So if you have open spaces, use A star. If you have bottlenecks, use CBS. The question is, what if I have both? So we have an enhancement here, or a generalization, which we call meta-agent CBS. And it's exactly like CBS, but we have added more lines in the following. After you validate the plans, if you see two agents which are highly coupled with each other, they had a lot of conflicts, let's merge them into a meta-agent. A meta-agent is just, it is considered by the algorithm as a single agent, only it's two individual agents in two individual locations. But in the low level, instead of searching for individual agents here, it will solve this meta agent. But the rest stays the same. And now the question is, should I merge, or who do I merge? And this is very related to the independence detection. Okay, if I see a number of agents which are correlated with each other, let's merge them. We tried a very simple merge scheme. When the number of conflicts already seen between A and B exceeds some threshold T, then merge them. There is also a continuum here, because MACBS, if you take T equals 0, which means always merge, this is exactly what Stanley called independence detection. If there is a small conflict, then merge them and solve them together. If you never merge, this is basic CBS, and I would like to say that a new direction might be to use some meta-reasoning methods here, or smart methods. What do I do? Some kind of stop, think, do I merge, don't I merge, do something dynamically. Reminds of the jumping policy of SFBDS, which could be done by meta-reasoning directions. We have seen that, okay, do I merge or don't I merge? There are many trends. I will skip it. I will summarize and then say something, another thing. At least in exponential, for optimal solutions, we have seen that A star is exponential in the number of agents, and it is best in areas with dense with agents. So versions of the tile puzzle will be solved more fast by A star variants. ICTS, which is exponential in delta, will be best in areas with open areas with few agents. CBS will be best in areas with many bottlenecks, but there is no universal winner, and MACBS is sometimes some kind of a continuum. For future work, new algorithms are coming. Like every conference, you could see new algorithms. But we still need, and personally, I would really be happy to work on this much more. Stop coming with new algorithms. Let's understand the existing ones better and the structure of the problem. How different parameters influence the different algorithms, the number of agents, the size of the graph, the branching factor, delta, density, all this has a lot of influence on the different algorithms, and we just don't know yet how. And of course, there are many, many ways to continue with developing more algorithms, more sophisticated algorithms, combining them, adding meta-reasoning, adding more enhancements, and so on. One last word I would like to, we are all AI people. An interesting problem that I'm collaborating with one of my colleagues, his name is Kobe Gal. He comes from the, I would say, more hardcore AI who deals with how do I combine computers and people. Think about you want to evacuate people, okay? We have a number of doors. Unfortunately, in our world, this is sometimes possible. We have a warning that in 10 minutes a bomb will fall on this auditorium. We want to evacuate as many people as possible. This is a multi-agent pathfinding problem. Now, as a search person, when I see this problem, I'm saying, okay, it's not exactly the same problem as we saw here, because every individual agent, I just want him to be outside. I don't care where. This door, that door, just go outside. So there are multiple goal states for everyone. Okay, it's an interesting search problem. But if we are talking about, so if it's robots, robots will do what I'm telling them. But what about people? Okay, let's say that I find an optimal solution, and if we hear that in 5 minutes there is going to be a bomb in this auditorium, I can calculate that I can, if everyone is doing what I will tell them, 90%, let's say we are 30 people here, I can save at most 25 people. If you all follow me, we have maximum utility because 25 people will be saved. And in order to do that, you go here, you go here, you go here. Are you going to obey this? Let me tell you this. Me, as the designer of this algorithm, I will be the first one not to obey it, because in this situation, I don't care about, everyone wants to save himself. I will run to the nearest door. Now, the nearest door policy is much worse than other policies. We have examples where you go to the nearest door, you save much less. So now the question is, and this is a combination, okay? This is a combination of search techniques, but you also have to be what they call in the other community, you need to be fair. The fairness criterion, which means you have to convince people to follow you. So I will maybe sacrifice the real optimal solution in the sense that I will convince people that there will be no worse with obeying what I'm telling them, okay? So it's a search problem from one side, but this is a hard AI machine versus people problem in the other side, just to give you a flavor of another aspect of this problem. I'm done. Thank you all for being in this tutorial. Both thank you by Nathan and myself. Let's all go to lunch. If you want to talk more, let's take it all offline. Thank you.